There's a process that happens in nature wherein microorganisms are consuming greenhouse gas. They're turning it into this replacement for plastic. This was effectively grown by microorganisms. This is what it looks like when it's extracted. I started looking at how could you collect methane? How could you turn it into useful stuff? There were a bunch of sort of initial ideas in terms of like, well, how do you even collect methane around cows? Well, cows are in many cases enclosed in barns, can use the ventilation air to do things that contain some level of methane. Well, now wait a minute, like there's other places that emit methane, maybe even higher volumes like landfills and abandoned coal mines and all these other places. So really the question was, what's the most useful conversion process? At that time, I also brought in a buddy of mine who was studying biomedical engineering at Northwestern. We were friends back in like sixth grade. We used to like TP houses together. My mom,
my son was ding dong ditching yesterday, and with his friends. I said, enough of this. Their neighbors are going to hate us.
Ding dong ditching, it's great. It's great for exercise.
Yeah, it gets him out of the house.
So we got together, and the basic conversation was, there's all this carbon going into the air. People are looking at this the wrong way. If we can turn this into valuable goods, we could potentially change the whole script here and create a really scalable pathway to helping to solve this. And so one of the things that we discovered in our early research was that there are microorganisms in the ocean and many other ecosystems around the world that are actually eating greenhouse gas as their food source all day, every day. Mm-hmm. A really good example of this is when there was the BP oil spill about a decade ago. There's a great article in National Geographic that talks about this. And the situation was all this methane was bubbling out of these leaks, but so much of it, for whatever reason, wasn't reaching the ocean surface. So it's like, well, where did all this stuff go? And what they discovered was that there were these microorganisms in the ocean water called methanotrophs. And these methanotrophs, or methane eaters, little microorganisms, bacteria in ocean water that were gobbling up the methane, using it as food just to grow. One of the peculiar things that we also found was that when these microorganisms grow, not only do they make, sort of what you'd expect out of a cell, their sort of cell walls and the basic operating functions therein, they make these little globules. And these little globules are energy reserves. You can kind of think of them somewhere between muscle and fat. Mm-hmm. But the microorganisms use it to kind of store carbon that they can use
in their bodies.
What we found was that it turns out if you extract that material and you purify it, it becomes meltable. And it turns out that the melt profile is actually very, very similar to the melting temperatures that we use today for plastic. And so all of a sudden we said, well, wait a minute. There's a process that happens in nature wherein microorganisms are consuming greenhouse gas. They're turning it into this replacement for plastic that, oh, by the way, because it's made throughout nature understands that it's fully biodegradable. Mm-hmm. And it's also a net carbon sink. It's reversing the flow of carbon. So in that National Geographic article, when they're talking about those methanotrophs operating, that's carbon going in the other direction, out of ocean water and into a solid material. So this was immensely compelling. We said, whoa, we could harness nature to create useful products from greenhouse gas. And so the next 5 years was basically looking for these microorganisms, trying to find ones that could operate at decent economics to get this done.
And are you in the ocean then at this point on boats? Like how are you identifying these?
Well, people ask all the time kind of where we finally found the ones that we use. It's worth mentioning, back then we didn't have any money. So we after graduating from college, we started working with a laboratory. We didn't have enough money to park close to the lab, so we would park far away and skateboard in, and we took odd jobs. I was a hotel bellhop, and Kenton was a valet, just scrapping together money to buy supplies and whatnot. And so we certainly didn't have enough money to go on some exotic. We weren't going to Antarctica or anything. So it's a local bug, a Southern California microorganism, and we were looking at ocean, estuary, anywhere that we thought these guys could exist. We take them back to our lab or our pilot plant, run screening on them, and just see what they could do. Mm-hmm. So finally, after a number of years, we found what we were looking for, and then had to kind of keep coaxing them to produce in the way that we wanted to hit the sort of performance that we were looking for.
Wow. Okay. So that was V1, really focusing on oceans. But I think stepping back, like, where are you today? Are you also focusing on that process? But I also think you do something with air carbon as well, correct?
Yeah. So in that process, we found a methanotroph, a methane eater, naturally occurring microorganism. Locally, it's found here in Southern California. And we now harness that bug. We use that bug to carry out our process. We also found that there's another kind of bug, a CO2 eater, that's called a chemoautotroph. And just like the methanotroph eats methane, this one eats CO2. So we developed those two natural microorganisms and put them into our process. So what we do now is we basically replicate, you can think of it like a slice of the ocean. We've got a big tank. We fill that with salt water, and then we add these microorganisms to that tank. And then we feed them greenhouse gas. That bubbles up through the reactor. It dissolves in the saltwater solution. And in that form, the microorganism can eat it and use it to grow. And then as it grows, it fills its cell with this polymer material. I've got some here. So this is what it looks like when it's extracted. By the way, most life makes this material, including the human body.
So that just came out of the microorganism? You extracted that out?
Yeah. So the microorganism grew this from greenhouse gas, and then we push that through a high pressure filter, and then it basically leaves this stuff behind. And then once it's dried, because it's meltable, we then run it into what's called a pelletizer. So we make these long strands and we chop those up, and that creates these sort of pellets that you see here. Once you have these pellets, you can put them into sort of a traditional plastic processing piece of equipment, and you can make all kinds of shapes and parts and pieces. We call all of this material, by the way, air carbon. So air carbon, anything made from greenhouse gas into this molecule. So one of the things that we make is something like a fork. So this was effectively grown by microorganisms, local, these are naturally occurring microorganisms from greenhouse gas, and used to make this part that can replace what would otherwise be a plastic part.
Okay, hold on. My mind is blown. I got to ask a few more questions on this.